In this section, we'll study scene analysis for noise data, and we'll consider a well-known algorithm called the RANSAC. Scene analysis is about the interpretation of acquired data, so it is a sort of a data interpretation. There are two subproblems. One is finding the best model, which is a classification problem. And the second one is computing the best parameter values. That is a parameter estimation problem. Here we'll focus on this second part. Traditional parameter estimation techniques, such as least squares, are trying to optimize the model to all of the presented data. But these techniques are simple averaging methods based on the smoothing assumption. The assumption is given here. There will always be good data points enough to smooth out any gross deviation. If you have a small number of data points, then some noise points will affect a lot for the parameter estimation. However, if you have many points, then even though you have part of noise points, it will be smoothed out so that your final estimation will be good enough. That is the smoothing assumption. However, this assumption is not really working for real data sets. In many cases, you have to include some internal mechanism to determine which points are matching to the model. And these points are called inliers, and which points are false matches. And those points are outliers or noise points. Let's see weighted least squares. We may try to use a least squares method, but now for noise points, rather than discarding those points, you may try to give some weights, smaller number. If you can see such partible points are reliable, then you can give a large weight. And for other noise points, rather than discarding these points, you may try to give a small weight. The reason it is realistic is here. For every data point, it is related with money. Data points will be obtained through paying some effort and money, so that in industry, usually they are really hesitating to discard a part of data points, so that once you understand the data set and some portion is reliable, then highly weighted, then you may get better estimation. The weights will be organized in this form, diagonal metric, along with the weights. And such metric W is called weight metric, and it can be decided either manually or automatically, but in most cases manually. Okay. Here is the algorithm. Okay, the given data, xi, yi, and there are endpoints. The best fitting curve can be found by solving an algebraic system given in this equation. Now you can apply a weight metric W, a diagonal metric. Of course, along the diagonal, And some points, some values are high and some values are lower. However, along diagonal, there's no zero, so that W itself is invertible matrix. And we can solve this system by using the method of normal equations. In order to do that, you just simply multiply X transpose. Then this matrix is a square and symmetric. Once the columns of X are linearly independent, then it'll be invertible, and you can get a unique least square solution. That is the algorithm for weighted least squares. Let's see this example. Okay, here in scatter plot, you can see red dots. I made this data set and almost linear here, and first one and last one are 2 points Y values are perturbed, so that it looks like noise. So once you recognize this, then for these 2 points, you may give weight 1/4. For these reliable points, just to try to give weight 1, and then try to get the line without weighting the output is this one, and with this weighting, the square line is that one. It is better than this one. Because of this point, it is a little bit, the curve is a little bit, the slope is a little bit becomes lower, but once you eliminate these two, then you'll get some line so that its slope is a little bit higher than this blank line. But anyway, if we give some credit, quarter credit for these 2 points, then that is the best fitting line. Okay. Now RANSAC, random sample consensus. It is one of the most powerful and most well and beloved algorithm dealing with point cloud data sets. Is used for reconstruction of ground structures, and we can say it is a 3D mapping. And from point cloud, we can understand the surrounding environment, and also we can map the environment. An example of getting the data points, the example, the device is, for instance, LiDAR. And LiDAR is usually producing more than 1 million points in each second. And by using that, the surrounding 3D geometry can be constructed. And once you are working on robotics or remote sensing, then you'll use this technique. It's very famous and now frequently used technique. So I hope you understand this technique very nicely. The RANSAC utilizes iterative search techniques for a set of inliers to find a proper model for given data. Okay, here, this is an algorithm developed by these two scholars in 1981. Okay, we'll go through this the steps. Before that, I'll try to explain this one pictorially. Okay, here we have presumably these are inlier points, and these are red dots are noise. then we'll try to get, for example, a line representing these inlier points. In order to do that, the first step is choosing 2 points randomly out of this whole data points, random 2 points. So the assume we choose this point and that point. Then now if the model is a line, then anyway here line can be constructed by using okay, let's try to do a little bit better way the figure. Okay, the line will be constructed passing these 2 points like that, and then with some number, and here in this algorithm we are using tau e, and we try to make a strip, and along with width is tau e, so that in both sides we are making tau e strip, and inside this strip try to find the points and count and number of points. So this is set and number of points are counted, and then now we do another one. For example, now I try to use another color, and in the second time again we are choosing 2 random points here, for example here, then that will be the line, and then we can make again tau e strip. Okay, and now count the number of points inside this strip. Once the red one, the number of points is larger than the blue one, then we try to keep the result from red one, and we keep going. Try to keep a larger one and smaller one is discarded and keep going. So that this is a kind of iterative search technique, and keep going, and once we reach a certain level, then we stop. Okay. In this case, if we know the number of inlier point in the portion, X, that sign means that total number of the points, and now inlier, this number of points is basically C absolute sign. Okay, that one, assume that is about 80%, then total number, and 0.8 is larger than 80%, then we can stop. So along with this stopping criteria, if we try to search again, then certain time later, we can reach at the required strip and inliers. Then by using those inliers, we re-estimate the hypothesis, the parameter, and stop. If not, then keep going. What if we don't know this one? So there sometimes we don't know which portion is really inlier points. In this case, we do in this way. Okay, we do this iterative search, and now we update number of points, and we keeping the larger one and keep going the iteration. But assume if it is really in the beginning stage, it is updated quite frequently. However, once it is reaching at optimal or almost optimal, then even though you do later on 10, 20 times iteration, it may not be updated. Then you can stop. Usually, about 10 to 20 times not updated, then the last result will be returned as the consensus said. So that's the idea. Now let's go back to the algorithm. In step one, select randomly a minimum point set as required to determine a hypothesis. Now, hypothesis, you may think this one is a model. So to determine model, you have to select randomly a minimum pointer set. Once your model is a line, then you may choose only 2 points. So you can get 2 points. That minimum set is 2 points. And you can generate a hypothesis. That is here the parameters. Okay. In fact, G function is making line, then rather than line itself, in fact, you need only the parameters, the coefficients. Okay. And compute the hypothesis consensus set fitting within the error tolerance. So the error tolerance, here, tau epsilon error tolerance inside. So from X, and by using this one, and then now here, along with the tolerance, is satisfies, then that becomes the set of points inside the strip. And we count the number of the points, and then once it is larger than certain one, then certain level, then finally, out of this set, try to get once more the hypothesis and stop. If not, then we'll go again. The iteration goes on. If we do that way, then here we may get this really good final result. Okay, so it is a one event. Okay, so from this data set, the RANSAC produced this one. Mathematically, the minimum pointer set is a set of 2 points because our model is regression line. Line requires only 2 points. Hypothesis, that is here y equal a plus bx, then we can write in this way, and then the equation can be made in this way, and so that eventually this is a pointer slope form, and b is the slope, and now from here, and we can get, anyway, we try to get, after getting this one, we reorganize so that we write down in this form. So these are parameters. Okay. Now, consensus set itself is collection of points such that from the point to the line hypothesis, the model line, and the distance is bounded by tau epsilon, which means that just the tau e strip inside the points are collected for the consensus set. Okay. In practice, step 2, the hypothesis P is the set of model parameters rather than model itself. And in step 3, we decide the inliers, the inlier points. And for that one, rather than collecting points, practically, we may try to use an array, there is index array, so that once ith point is in the hypothesis, then ith value is 1, otherwise the value is 0. So rather than practically collecting the points, here we try to use an index vector to indicate the points corresponding to value 1 are in the consensus set. Okay. And also this technique can be considered as automatic weighting mechanism. Inside the strip, it is considered for the least squares algorithm. Outside is ignored, so that eventually, now from xi and the model, the distance is bounded by tau epsilon, then it looks like we are setting weight is 1, otherwise weight is 0. So this RANSAC can be considered as a weighted least square method, and also the weighting mechanism is automatic. You may consider this way. RANSAC is based on iterative search, so that and just repeatedly we try to search so that each search portion is not difficult to implement. So the overall algorithm is quite simple and also efficient. However, it is problematic and often erroneous, because after a certain number of search, it stops, so that the output, after finishing one round of the computation, the output is not really the same, which means that RANSAC algorithm is not repeatable, is unrepeatable, and it may yield different results in each run, so that none of the results can be optimal. Look at here. Now, this data set, and a little bit tense one, the total number of points is 250. For that one, 1,500 points. Once you are using all the points, then you'll get this red least squares line. Once you try to use all the inlier points, then this blue line. And RANSAC is producing this one. This is an example from one run. But if you try to run several times, and you can see some result is matching this one very nicely, or sometimes you have a little bit different result. But anyway, each run produces a different result. So it is not repeatable, which means not optimal. For larger set, also the same is happening. So here, I ran RANSAC 1,000 times for this data set and that one. And then for the model A0, A1, I try to measure the mean out of 1,000 runs, and from 1,000 results, A0, A1, and for each one, I try to find the mean and standard deviation. Standard deviation is large, which means that if it is large, then that means it is oscillatory. Each run produces different solution, right? Okay, here. Now, that one, and for A value, there's intercept, and for this one and that one, okay, almost same, 0.1. Standard deviation is 0.1. That means in intercept, 0.1 is just fluctuating and very frequently. And for slope, okay, once the slope is changing even small, then overall in here, long distance, so that it's a lot changed. So that change in the slope is small in quantity. However, it's not really small. And small change makes a lot, because it's covering from here to there. So that this means anyway is quite fluctuating. Now this is elapsed time somehow, and for this one, the RANSAC built-in MathTalent is faster than for that one. Somehow it is happening. But anyway, this is output from the MathTalent built-in RANSAC algorithm. Okay, here we have a sort of a conclusion. The RANSAC is neither repeatable nor optimal. In order to overcome the drawbacks, various variants have been studied in the literature. Nonetheless, it remains a prevailing algorithm for finding inliers, and there are here I'm showing you here only 3 of them: BLESAC, PROSAC, recursive RANSAC, and also there are many others. Yet it is still unrepeatable and is not optimal. And recently, an optimal variant of RANSAC is suggested by these people, and the last author is me, and early this year it is published, and the name of the algorithm is Iterative Update Sample Consensus. So it is called IUSAC. The IUSAC is a few times more effective in both accuracy and efficiency than RANSAC and its variants. Is optimal, and optimal means that the result is always the same. So it is converging to certain one rather than iterative search. It is from some initialization, it is try to now iteratively update so that eventually it is converging to the optimal solution. So it is an optimal variant. Okay, that's the end of the section. Thank you.